So the removal of a vertex, we're going to refer to this as G minus V. And what this basically says, let G be a graph where, or with, V is the element of the vertice set. Then G minus that vertice is the graph obtained by removing that vertice from it. Okay, so at the moment, not too bad. It's saying, hey, you have this graph, the original graph, and now you're removing that vertice from that graph to create a new graph. So let's do an example. So let's have our original graph, G, and let's do that. Okay, V1, V2, V3, V4, and V5. And what we're going to do is we're going to remove V2. So we're going to have G minus V2. And if we do that, we still have V1, we still have V5, we still have V4, and we still have V3, and we have all the edges and stuff that were associated with V1, V5, V4, and V3. So when you think about it, when you're removing a vertex, you're creating a subgraph, and you're creating a vertex-induced subgraph, where your vertex that's inducing it are all the leftover ones. So you still have that edge, you still have that edge. Okay, so it's basically like a vertex-induced subgraph that you're going to have. And however, obviously, because V2 is gone, all the edges that has an end, V2 as an end vertex no longer exist. And that's actually a very important thing to notice and to think about, because that's obviously going to change the way that you describe the order and the size of this subgraph where it's minus that vertex. So the order on this one, on just G, was 5, right? And the order on the one where you just removed one vertex is 4. It makes sense, you removed one vertex. But now the size is actually going to be quite largely impacted, because you are going to have the degree of, the one you're removing. So yeah, in this case, it's a degree of 4. And it's going to be completely gone from your next graph. So you have a case of your size of your first graph, and let's just count it out. 1, 2, 3, 4, 5, 6. So you have a size of 6 happening there. But now let's just count it out again for this graph where you remove vertex 2. It's just 1 and 2. So we have a size of 2. What's actually happened is you removed the degrees of V2 from your size of your graph. So how can we write this in, general arbitrary terms? And the idea behind this is you say, okay, we're going to have the vertice set be in order n. So we're going to have some vertice set, and it has n vertices in it. Then your new one, the G minus that vertex, and again, this is just in general now, it's just n minus 1. So we've seen that. We see order 5 and order 4. Then we're going to think about it and be like, okay, the vertex that we're removing has a degree. And we're going to say that that vertex's degree is p. You're just going to give it a p-value. I know it's 4 here, but remember, we're generalizing it now. And then we say, okay, we also know what the size of the original graph is. So we know that it was e.g., the absolute value signs basically, but the order of that is m. So the size of the graph was m. It had m edges in it. And now we noticed that what happens is we subtract the degree, because we're removing all those edges. We're removing p edges. In this case, it was 4. We removed the 4 edges here. So when we work at the size of the new graph, it's the size of the old graph minus the number of edges that were connected to the vertex we're removing, in other words, the degree of that vertex, to get it. So our EG minus our V is actually our original size minus the degree of the one that we're removing. So here we have some general terms that we can use, and we can always work it out. So we don't have to draw it all the time. We can work it out straight from there. So that actually gives us, a theorem that says, hey, if we have this order, and we have the size, and we have the degree of the vertex you're removing, you can find the order and the size of the new graph. So let's just write that down in terms, or meter basically. So let Vg equal n, and the degree Gb equal to p, and the size of the graph equal to m. Then the order of the new graph, G minus that vertice, that's curly brackets, I know it doesn't look nice, is equal to n minus 1, and the size of the new graph is equal to m minus p. And we saw that with our example. So now we're going to do the same thing, or not entirely the same thing. We're going to follow the same approach, looking at what happens if we remove an edge. And then we're going to get an edge-induced subgraph, and what happens with the orders and sizes there. Okay, so if you remove an edge, we basically say G minus E. So we say let G be a graph with E an element of the edge set. Here we work with simple graphs, but it could be element of a multi-set. And then G minus that edge is the graph obtained by removing the edge E from that graph. Okay, so this definition again, pretty obvious style definition. And we're going to go through an example. So let's draw a graph. I don't want to draw it in the same color. Okay, so there we have our graph, and let's just call that V1, V2, V3, V4, and V5, and let's give this as E1, E2, E3, E4, and E5. It's not necessary to label them, but it just makes it a little bit easier to discuss. That's graph G, and we're going to go say graph G minus, and let's remove E2. Okay, or if you wanted to write this in other notation, that's V6. Minus V2, V6. Okay, so there is a way that you can write it without labeling all your edges. Okay, so let's go ahead and draw that. So if we just remove E2, we still have all our edges that are left over. But one of the things to note is just because an edge is gone doesn't mean that the vertice can't exist, because you need the vertices to make up an edge, but you don't need edges to make up the vertices. So the idea behind this is, if you remove an edge, you're only removing the edge. That vertice can still chill there. Right. So let's look at the order and sizes of these graphs. So the order of this one is 6. And the order of this one is still 6. The size of this one, well, we had E1, E2, E3, E4, E5, so it's 5. And then we have the size of this one is just 4. So one of the things to note here is that when you remove an edge, the only thing that changes to your graph is your edge is removed, which means the only thing that changes in the structural identities or stuff of the graph is that the size changes. So here we have this case of, we have Vg equals to your n, and your Eg equals to your m. You're going to still get Vg minus that edge. And again, we're just looking at the arbitrary case there. There is still n. Nothing's going to change to it. And then your size, Eg minus your E, is just going to be down by 1. Okay, so we've gone through what happens to your graph when you move vertices, what happens to your graph when you move an edge. So when you remove an edge, the structural integrity of the graph in terms of its vertices remain because your vertices don't need edges. But for an edge to exist, it needs two end vertices, which is why the structural integrity, kind of like changes. The shape of the graph changes in that vertices and stuff remove, and the order and stuff can be messed around if you remove a vertice. So that's just a very important concept to understand and to grasp.